Hey MathHL, in this video we are going to talk about the vector equation of a line, parametric equation of a line, and the Cartesian form of a line, specifically like when we're working with vector problems. So we're looking at three different forms that all represent the same thing. First, let's talk a little bit more about the vector form of a line. So you'll notice here that we have three vertical matrices. We have xy. Here we have x1, y1. x1, y1 is just any point on the line. So you and your neighbor might have different numbers in those spots, depending on which point you or she or he used. Then we have a scalar, k, so like 2, 3, 5, -1. Then we have another vertical matrix, and this represents the movement of the line. So if we want to think about it, we call this the direction vector. That's why they're calling it D1 and D2. It's called the direction vector. And what D1 represents is it represents the movement of x, so how x changes. So this would be D1 units in the x direction. And D2 represents how many units you're moving in the y direction. It's kind of like slope, except instead of rise over run, this is the run and this is the rise. So it's kind of backwards from what you might be familiar with. If we think about what this means geometrically, we can think of it this way. Let's say we have some starting point, x1, y1, and we know the direction that the line is moving in. Let's say it's moving 3 units left and 4 units up each time. So I'll just guesstimate where that would be. So let's just say that's after 1 unit of time. So after k, if k equals 1, let's say, our line is now here. But then it does that multiple times. 3 units to the right and 4 units up again. 3 units to the right and 4 units up again. We can actually also do this backwards. 3 units to the left and 4 units down. So from that starting point, we can move either in the positive direction for like k equals 1, k equals 2, k equals 3. We can also move negatively, like k equals -1. And that would take you to each of these three spots. So if we put those all together, what do we get? A line. So that is a very useful way of representing movement. And in a future lesson, we're actually going to do that. We're going to use actual application questions and talk about the equation of a line in that sense. So the second way that we're going to write out lines is in parametric form. Parametric form is simply when you separate the x and the y into their own equations. So for example, x equals x1 plus k times d1, and y equals y1 plus k times d2. So you look at the top row of your vector and then the bottom row of your vector and just write them each separately. If there was a third row for our vector, that would be z. So if we had z, we'd have z1 here and then d3 here. So we would just add one more part to parametric form. So these together are considered parametric form of the line. Cartesian form is when we put them together into one equation that looks like an equation we've worked with before. Pretty much all of the math that you do up to this point is in Cartesian form. So what we do in order to translate from vector or parametric into Cartesian is we start by getting k alone in each of our parametric forms. So if I got k alone here, I'd have x minus x1 divided by d1, and then y minus y1 divided by d2. And those are both equivalent to k. And so because they're both equivalent to k, we can set them equal to each other. So I'll have x minus x1 over d1 equals y minus y1 over d2. So this is the standard form for Cartesian form of a line, except that's not actually how we're used to looking at it, right? We're used to y equals mx plus b. This can be rearranged to be in that form. You would just get y alone. So if you wanted to see what this looks like in slope-intercept form, you would just move things around so that y was alone. Okay, let's take a look at an example, and we're going to write the equation of the line passing through these 2 points in vector, parametric, and Cartesian form, all 3. So the first thing I want to do is I want to figure out what our direction vector is. So the direction vector can be found by asking ourselves, well, what do I do to 3 to get 6? So our direction vector is going to be 3. And then what do I do to negative 7 to get 5? So 3, 12. If you want to, you can simplify this by dividing them both by the same value, 3, and we can get 1, 4. Okay, so vector equation of this line, we're going to have xy. The next thing we put is a point. It does not matter which point we use. I'll just use 3, negative 7. You just as well could have used 6, 5. And then we'll do plus k. And then we'll do our direction vector 1, 4. So this is the simplified version of the vector equation of this line. Okay, parametric is next. So to write the parametric equation of this line, we simply take the top row and bottom row and separate them. So x equals 3 plus 1k. Y equals negative 7 plus 4k. Okay, 2 are done, 1 more to go. The last one we're going to work on is the Cartesian form of the line. So what we do is we get k alone for each of these. So here we'll have x minus 3 equals k. Here we'll have y plus 7 over 4 equals k. And then we'll simply set those equal to each other. So that's the Cartesian form of our line. So the Cartesian form of our line, when we're working with vectors, is always going to be x or y plus or minus something over a number. And there might potentially be a z over here as well. Let's say we wanted it to be in slope-intercept form. It doesn't, oh, it does say also find the slope-intercept form. Simply get y alone. That's all you got to do. So multiply the 4 over, subtract the 7. There's slope-intercept form. So when we say Cartesian form, technically both of these are Cartesian form. But when we're working with vectors, we most normally write Cartesian form of lines this way. And the reason we do that instead of slope-intercept form is that when we're working with 3 dimensions, there is no slope-intercept form for that. So we can only write it in this form for 3 dimensions. Speaking of, I think that's the next one. Nope, we're going to do that in a minute. Next one up, find a vector equation of the line that passes through the point 1, negative 4. So that's going to be our x1, y1 in the vector equation of the line, and is parallel to. Well, if it's parallel to that vector, it's going to have the same direction vector. It will be moving in the same direction. It may be higher or lower, like for example, these pens are in different locations, but they have the same slope. They have the same direction. They're both going over, let's just say 8 and up 4. Over 8, up 4. So we can simply plug this stuff into our vector equation form. So I have my point here, 1, negative 4. Now, the variable we use for our scalar here, the letter we use for our scalar, I should say that, we can use k, but you can also use other values or letters like t. T is a common one as well. So just to illustrate that you can use different things, I'll put a t this time. And we had 1i minus 3j. So there we go. Okay, next one. Find a vector equation of the line that passes through 1, negative 4 and has a normal vector, 1 minus 3i. This terminology is likely new. Normal is another way of saying perpendicular. So the vector that it's perpendicular to is 1, -3. Well, if we want to make a perpendicular slope, we do the opposite reciprocal. Same thing here. We just switch our x and y, and if the net value of this was negative, it will now be positive. I'll talk about the other case in just a second. Let's write the equation out. So we'll have xy equals 1, -4. Sometimes they use s, so maybe I'll use s on this one. And 3, 1, like so. So going from where it's a negative net value, meaning if I think of this as a slope, it'd be -3/1. So the net value of that fraction would be -3. The opposite reciprocal, that would be 1/3, or as a vector, 3, 1. But what if my original vector was positive, positive, and they asked the same question? How do you make a normal vector if the net value of the original was positive? Well, what you do is you either put the negative with the 5 or with the 2. It actually would be okay either way. So either way, if you wanted to make a vector perpendicular to 2, 5, you could either use -5, 2 or 5, -2. So you flip it over and you put a negative on one of the values, okay? So that's just a little side note. Next one, let's talk about the angles between lines. We'll also get a chance to write things in switch from Cartesian form to parametric and vector form. Because so far we did vector form, and then we did parametric, and then we did Cartesian. But what if you had to go backwards? How do you go backwards? Okay. We'll also talk about how to find angles between lines. We need, in order to find an angle between lines, we need to write it in vector form. So right now we're in Cartesian form, and I can see that that is the case because of the pattern in which these are written. This really has a 1 on the bottom, right? So what we're going to do is we're going to go from Cartesian form to parametric to vector, the opposite direction we went last time. Once we get these things in vector form, then we can find the angle between them. Okay, so how do we do that? Let's start with line 1. What we'll do first is we'll think about what we did before. When we switched to Cartesian form, we took our scalar, got it alone, and then see how we eliminated the scalar? So what we need to do is go backwards. So we're going to take each component of our Cartesian form and set all 3 of those equal to some scalar, k, t, s, whatever we want to do. So I'll say maybe k. So k is equal to x minus 5/3. K is also equal to y plus 1/4. K is also equal to z minus 4/12. Now what I'm going to do is I'm going to put it so that the x, y, and z are alone, so that it will look like this, parametric form. So I'm going to multiply the 3 over and add 5. I'm going to multiply the 4 over and subtract 1. Multiply the 12 over and add 4. So this is the parametric form of my line. Now lastly, let's put that into vector form. X, Y, Z, because I do have a third component now. The point comes from the constant in each of your parametric components. So we're going to have 5, -1, 4, plus k. And then my direction vector comes from the coefficient of k. So 3, 4, and 12. So that is the vector equation for line 1. Now we'll repeat that process for line 2. So I'll set each one of these equal to some scalar. I will say I'm going to pick a different scalar, not k. I'm going to pick a different one. So let's pick t this time. So t equals x minus 4 over 2. T equals 5 minus y. T equals z minus 20 over negative 2. Next, I'm going to get x, y, and z alone so that I have parametric form. So I'm going to multiply by 2 and add 4. Here, I'm going to swap these places. I'm going to move the y over here. So I'll move the t over. So I get negative t plus 5. I'm going to multiply by negative 2 and add 20. So now I have parametric form. Lastly, let's put this into vector form. My constants make my position vector. I'm using t as my scalar this time. And then I use my coefficients 2, negative 1, negative 2. And that's my direction vector. So this is how you can switch from Cartesian to parametric to vector. Notice that parametric is sort of the middleman. We have to go through him to get from vector to Cartesian or from Cartesian to vector. Now that we have them both in vector form, this is when you can find the angle between these two lines. And what we do is we look at the direction vectors of the two angles. So we're going to look at 3, 4, 12 and 2, negative 1, negative 2. To find the angle between them, anytime you're asked to find an angle, you immediately want to think dot product. We're going to find the dot product between those two direction vectors. So remember, we have the two definitions of dot product. One is the algebraic definition, where you multiply the x's, you multiply the y's, and you multiply the z's. The geometric definition is the magnitude of each one multiplied times cosine theta. So I need the magnitude of this. So I'll do a little side work here. Nine plus 16 plus 144. I get 169, and the square root of that is 13. And the magnitude of my second line, 2, negative 1, and negative 2. So I'm going to get 4, 1, and 4. So 3. So I've got a 13 and a 3 cosine theta. So I'm just using the dot product or scalar product formula and substituting in the information from my direction vectors. And now we work it out. So 6 minus 4 would be 2, minus another 24 would be negative 22, over 39. Since this is negative, I can anticipate that my answer will be obtuse. I do not know if I'm in the right mode or not. Let me check. I want to be in degrees for this. That's typically how we measure the angle between things. So 124 degrees. That would be 3 sig figs. 124 degrees. Okay. So basically what's happening is that you have some sort of line doing this, some sort of line doing this. It's in 3 dimensions, but I'm drawing it, so that we can see. 124 degrees. That's what that angle would be between the lines. What would this angle be? 56, right? So sometimes they will ask you for the acute angle between the lines. If they use that specific language, find the acute angle between the lines, then you must give the acute answer. So if you get the obtuse answer, then you would just say, well, subtract from 180 and I'm good to go. And in fact, if I was wanting 3 sig figs, I would need 55.7. All right, so that wraps up this video about the different forms of the equation of a line that we can use, and also how we find the angle between lines using vector form. Okay, that's it.